We're going to be looking at RF1 quadratic functions today. We're going to start off the beginning of our quadratics unit, so relations and functions. So first, to start us off, what is a quadratic function? Well, a quadratic function is a second degree polynomial function. Right, so that being said, we are seeing lots of squares as our largest coefficient on x. Right? We can see other terms too. We can see x's, we can see constants. We just can't see anything larger. Right? The degree of a function is the largest exponent. So since these are second degree, the largest power we see on any variable is a squared. Right? We focused a lot on first degree functions last year in Math 10C. Sometimes we called those linear functions. That's where our highest degree was 1. That's where we were looking at straight lines. Right, now that we don't have straight lines, now that we're going to be squaring some values, our graphs and our functions are going to start to look a little bit different. So here we have a couple of examples, right? As we see, we have an x squared term on both of these. They're always going to be polynomials, meaning those powers always have to be whole positive numbers, no fractions in our exponents. But we can have coefficients that are positive or negative. We can have constants that are rational or irrational. We just have to have that x squared hanging out somewhere. So what does one of these look like? Let's start with our most basic quadratic function, y equals x squared. So when I'm looking at a table of values, right, again, I'm saying what x is related to what y values. And in this case, it's saying, right, remember an equation is like a set of instructions. If our equation is y equals x squared, it's saying, well, hey, I can find a y value by taking an x value and multiplying by itself, right, by squaring it. So if I take an x value, of -3, the resulting y value is going to be what happens when I take that -3 and square it. And I'm going to get a +9, right? -3 times -3 gives us a positive result. And then how this point translates to a graph, right? It's an ordered pair. We a lot of the time see it written like this, as a -3 and then a +9. Right, that's how we express those coordinate locations. X is first, y is second. So all three of these things, right? The equation y equals x squared, the table of values where we have our x's and y's, and then the list of points we're going to connect together are all just representing this same function. So I'm going to plot the point -3, +9. So I think, okay, well, I go -3 along the x-axis, and then I go +9 on the y-axis, and that's where my point is located. But this graph is more than just a single point, right? It's every x that when I square it, it gives me a y value. So let's look at a few more. When x is -2, I go ahead and I square that, right? -2 times -2. Y is +4. So again, I'll graph that. I'll find -2. I'll go up to +4. That's another point on my graph. When x is -1, well, -1 squared, -1 times -1 is +1. And 0 squared is just 0. 1 squared, +1 squared is also +1. And +2 squared is also +4. And +3 squared is +9. So notice we kind of get this interesting effect where the numbers start to repeat themselves. And that's because that effect of when I square a negative number, I get the same result as when I square the positive version of it. Right? I can't get a negative result when I'm squaring a number because it's negative times negative gives us positive, or positive times positive gives us positive. So I plot these points, -1, 1, I have a point at 0, 0. I'm going to erase these little guiding points I used. +1, +1, +2, +4, and 3, 9. So we're going to notice that these points give us this interesting shape. Let me try to do that a little better. When I connect them all into a nice smooth curve, we get this shape that we describe as a parabola. Right, or we can say the shape is parabolic. all that is a name for this U-like shape, right? It's a quadratic function, but quadratic functions take the form of a parabola, just like linear functions take the shape of a straight line. All right, so there it is. The graph of a quadratic is a parabola. And so we're going to look at, this is our most basic one. This is just x squared. But we can have lots of other things. We can talk about 2x squared, or we can talk about negative x squared plus 5x. Right? They're all going to take this general shape. And we'll see how things kind of twist and turn depending on what we add in there. So with these quadratic functions, we can express them in three main forms. We can talk about it in standard form. And standard form is the easiest we use for solving equations. That takes up the form y equals ax squared plus bx plus c. This is just a general standard expanded trinomial function. Right? We've looked at some things that look like this in the past when we did our factoring unit. We can also see things in vertex form. Vertex form looks like y equals, notice there's still an a value, and again, a, b, and c are just representative of numbers. This one looks like x minus p squared plus q. And this is still a quadratic function because if I was to expand out that x minus p all squared, I would end up with an x squared. The x is just kind of disguised in this one. And notice that instead of b's and c's, we're talking about p's and q's, which represents that they're representing different points, right? B and C and P and Q are two different characteristics of the graph. And then the last one is factored form, and that generally takes the form of y equals x. Oh, sorry, let me put that a out front. I almost lost it. A x minus h, x minus k is how you'll often see this. Right. And so what this is we have two linear factors, right? Notice that again, there's no x squared, but if I was to go and multiply the x by the x, it would turn into an x squared. So again, it's kind of disguised. It's been hidden because we pulled things apart, but if we were to multiply them back together, that squared would still be there. And factored form is especially useful for solving. Let me just hit enter so we can see all this. Specifically for the roots or zeros or X-intercepts, and we'll talk about all these different things. But these are the three main forms we're going to be looking at. And again, those A's, B's, C's, those variables other than X and Y will be filled with values. So let's talk about the characteristics of a quadratic function. There's some main points that are extra important to us, generally because they represent a significant point. Right? They talk about some important aspect of the graph. And we've talked about some of these aspects when we talked about linear functions as well. So X-intercepts, we've talked about before. These are the points where our graph hits the x-axis, right? Where it intersects that horizontal axis. Similar to that, our Y-intercept is where our graph intersects the y-axis, that vertical axis. So we've seen these before when we talked about linear functions. Because we have this fancy new shape, this parabola, instead of a straight line, we have a few more important things. We have the axis of symmetry. So it's actually kind of an invisible line. It's not a real line. But remember, when we talk about symmetry, that's us talking about where I'd be able to draw a line and have everything meet on either side, right? A true reflection. So here, because we have that parabola shape, right, and it's the same on either side, if I was to fold this graph right down the middle, right, those two arms, those two sides would meet up. That's the place where we have symmetry. I can't draw a line anywhere else and have everything be perfectly symmetrical on either side. And then we have another new point that we call our vertex. And so the vertex is this little point on the graph where essentially it changes what it's doing. This is where that kind of bounce effect happens. So it was kind of decreasing, right? If we were reading the graph left to right, from the left side over to the middle, the graph is decreasing. It's going down as I look further right. Then we hit that vertex and it kind of swings up to the other way. As I keep going right past there, now it's increasing. We're going to have two possibilities for our vertex because that depends on direction of opening. So we have a parabola like this U shape. This is something that we say opens up. However, when we change some values, and we'll see which values affect this, we can also have this thing flipped upside down. And we can end up with a parabola that opens down. The main thing to notice there is that our vertex is either the lowest point on the whole graph there. We sometimes call that a minimum. Or when our graph is flipped upside down, our vertex is actually the very top, right? It's kind of like a peak of a mountain, a peak versus a valley. And we call that a maximum, right? So it's just ways to describe our vertex. We also in the past have talked about domain and range. Remember domain, it talks about all the possible x's. Right, so essentially how far left and how far right will this graph go, ignoring any vertical change. And then the range, we talk about our possible y's. Right, where does this graph exist? How far does this graph go up and how far does it go down? What y's are we able to get as a result? So first thing first, we're going to look at standard form. And the first thing is to identify those variables, A, B, and C, right? So standard form in general, we have ax squared plus bx plus c. And we call them A, B, and C to help us identify them. And because A, B, and C can tell us specific things about the graph. So in this first one, A is 4, right? A is that coefficient in front of our x squared term. Right, we can try and trick you by moving things around, but A is always attached to the x squared term. B is that thing in front of x. So our B value here is 3. And then C is our constant term. Right, there's no x at all. And so our C sits on the end there. Our C here is 2. So when I continue to look at the next one, right, we found our constant term here. Again, A is the coefficient in front of x squared. Now be careful, we want to make sure we include the sign. So here A is -2. B is going to be +3. And C is going to be -1. So take a minute, pause, see if you can identify A, B, and C for our last example. Right, so we should get that A here is +1. It can be tricky when we don't see a coefficient, but remember that an invisible coefficient is always a factor of 1. B is -2, right? Again, keeping an eye on the sign, we have only positives in our general form, right? ax squared plus bx plus c. So if we're seeing subtraction, that means we're actually adding a negative version, right? So here we're adding -2. That's telling us that b is -2. And c is +1 in this last one. So why is it important to find A, B, and C? Well, like I've said, they tell us different things. So our A value tells us two main pieces of information. It tells us the direction of opening. So it's going to help us figure out, does this graph open up or does this graph open down? It also tells us the vertical stretch factor. And what that means is it's telling us, right, how much our graph has been pulled or pushed in a vertical direction. Right? Picture grabbing an elastic band. If you stretch it vertically, the sides are going to pull in. It's going to get more narrow. And if you push it down from the top, it's going to get more wide. A couple of things. If A is negative, that's where we see those parabolas that open down. All right, and like we said, that means the vertex is now going to be on the very top of our parabola. So we have a maximum value. So all of these things just stem from us saying, is A positive or is A negative? When it's positive, the opposite is true. So when A is positive, our parabola, our quadratic function opens up, right? We get that U shape. That means we have the valley, right? The vertex is at the bottom. So our vertex is a minimum value. And then the value of that, right? A, we're just worried about sign right now, but in general, if A has a value of 2, we say it has a stretch factor of 2. And we're not going to be super concerned with that. We're more worried about the direction of opening. So 4x squared plus 3x plus 2, when it's asking us which direction do the quadratics open, we know we're only concerned about A. We haven't talked about B and C yet. And B and C don't change our direction of opening. So if this graph has an A value of 4, and it's a positive 4, that means it's going to open up, right? Because we have a positive A value. It also has a stretch factor of 4. So it's stretched 4 times as much. Looking at our second function, notice now that our A value is -2. So that's going to tell us, fix that, that's going to tell us that it actually opens down because we have that negative value. We can still say that it has a stretch factor of just 2 because the negative already told us it actually flips upside down. And then in the last one, our A value is +1. So again, because it's positive, it opens up. When we talk about stretch factor, we're saying how many times are we multiplying it by? Well, in this case, we don't really have a stretch factor because our value is 1. We multiply something by 1, it doesn't change. So now that we've talked about what A does, let's skip over B for a minute. Let's talk about what C does. So C tells us the Y-intercept. So the C value is going to help us figure out where does our graph hit the Y-axis. Y-intercept. So the location, the coordinate of our Y-intercept is always 0 and then C. Again, 0 because when we talk about a Y-intercept, the whole point of it is that it's on this Y-axis somewhere. And every point on that Y-axis has an X value of 0. Write that a little clearer. Because we're on that Y-axis, that means we haven't moved left or right from the origin. So we always have an X value of 0. So the C value tells us how far up or down on that Y-axis we are, right? It tells us the Y value. In general, this is also the starting height of some sort of projectile. We can describe this as saying this is usually our initial value, right? Because it's when we have an X value of 0, and X being our independent variable usually talks about things like distance or time. And when we talk about starting something, it's usually at a distance of 0 or a time of 0, and then we progress from there. So this point in context usually represents an initial value. So looking at some quadratics, we want to find the Y-intercept. So again, we're looking for that C value here. We don't care, right? Opening up or down won't affect that. The B value won't affect that. It's always just 0, and then our C value, the constant on the end there. Keeping in mind that if the sign is negative, then the sign is negative, and that's okay. We can keep that in there. 0, positive 1. If we don't have a constant term, that doesn't mean we don't have a y-intercept. That just means that our y-intercept is at 0, right? It's at the origin. In terms of x-intercepts, we're going to come back to this when we start to use our calculator. B value, so the last thing, it doesn't actually tell us anything, but we can use it to help find the position of the vertex, right? So B kind of moves our parabola shape around the graph, but it's not in a very explicit way. So we do have this fancy formula that can help us find the x-coordinate of the vertex, but we then have to figure out the corresponding y value, right? Because the vertex has an x and a y value. So we're gonna glaze over this a little bit. Instead of talking about the coordinate of the vertex, I just want you to tell me the b value. So for this first one, y equals x squared. Well, remember the b value is the coefficient in front of the x term. If I have no x term, then I have no b value. My b value is 0. If I was to use that formula, x equals negative b over 2a to start to find my vertex, well, I'm getting the 0 on the top of that fraction. That's already going to tell me that the x-coordinate of my vertex is at 0. Looking at my next one, again, I'm looking for the b value, so in front of the x term. In this case, my b value is 8. So if I wanted to find my vertex, or at least the x-coordinate of my vertex, I'm going to plug in b into the top. So negative b, I put in negative 8 over 2a. So in this case, a has a value of 1, right? Notice b doesn't tell us anything on its own. We have to be using some other parts, whereas a and c just straight up told us information. So I do negative 8 divided by 2. This is telling me that my x value is negative 4. This can also help me find my axis of symmetry, because that's always going to cut right through the vertex, right through the middle of my parabola. The last one, b has a value of 6. So again, if I was to take negative 6, right, again, the negative is part of the equation, over 2, a in this case is negative 1. I get a positive 3. So again, that's telling me the x-coordinate of my vertex. We'd have to do some extra work to find the y value, but we won't worry about that just yet. So that's where we're going to stop. We've analyzed A, B, and C in standard form. In the next lesson, we're going to go through some examples. We're going to say, how can we use A, B, and C, as well as our graphing calculators, to help us sketch this graph and find out all the information we need.